Assalamualaikum and hi, we are from Group 1. So today we will present about our lab experiment 1, which is stability of floating bodies. So we are in Group 1, which consists of me, Aina and Abdullah, the leader for this week. And then we have also have Ahmad Diawuddin Arif bin Shihabuddin Arif. And last one we have Chiu Siying. So next, I will pass to the next presenter for report summary.
Assalamualaikum. My name is Ahmad Diawuddin and I will carry on the report summary for this experiment. Experiment 1 is an experiment regarding the stability of floating body. Stability of floating body experiment is an experiment to determine the height of metacenter using the tilting method. It is intended to illustrate the stability of floating cylinder and to demonstrate the principles of buoyancy, metacenter, and metacentric height. A floating body's center of buoyancy, C, is determined by its form and the direction at which it is floating. Since the form of the underwater volume varies when the body is disrupted by a slight angle of yield, the center of buoyancy changes. This center of buoyancy at the center of gravity of the fluid displaced by the vessel. The metacenter, M, is the point of convergence of the lines of action of the buoyancy force before and after heel, and the metacentric height is the difference between the center of gravity and M. Next, we move on with the objectives of this experiment, which is stability of floating body experiment is an experiment to determine the height of metacenter using the tilting method. Now I pass on to the next presenter.
Hello, my name is Xiying, and I will continue to present about the theory part. The knowledge on the stability of pontoon such as a floating ship is vital. As depicted in figure below, a floating body can be stable even though the center of gravity CG lies above the center of buoyancy C. This is true since as the body rotates, the buoyancy force FB will act on the central C-prime of the new ball displacer, which then form a restoring couple with the weight W, hence cause the body to return to its original equilibrium position. However, for the relatively tall, slender body as shown in figure below, a small rotational displacement can cause the buoyancy force and the weight to form an overturning couple, which lead to the unstable configuration of a floating body. In this experiment, the stability of a pontoon is determined with the center of gravity at different heights. If a horizontal weight is moved with a distance fs from the center, the pontoon will tilt. The angle of tilt can be measured by using the palm board. Next, I will pass to Adrian. That's all for me. Thank you.
Hi, my name is Adrian. Now I'm going to present about the procedure. First of all, we remove the horizontal weight and fix the height of the vertical weight of the mast of the pontoon. Next, we determine the center of gravity by putting the pontoon mast on the pontoon stabilizer. We measure the length of the center of gravity, which is the half distance from the base of pontoon to center of vertical weight. We fix the horizontal weight and ensure that the thread is at 0 mm positions. Later on, we fill the tank with water and we place the pontoon inside. Next, we measure the length of the pontoon which is submerged in the water. And later on, we move the horizontal weight to 10 mm to the right and record the angle of tilt of the thread. We repeat the step again, and this time we move to the left. And last but not least, we adjust the height of the vertical weight to a new height, and we repeat the whole step again. We do this test for 2 different values of vertical height. Next, I will pass to the next presenter.
Next one, it's with me again, Ahmad Jodin for data analysis, and we will start with the basics. This is the table for which we recorded our findings. In this, we will need to calculate the GM, which uses the formula small w times x over capital W tan theta. The small w is the mass of horizontal weight, which is 0.28078 kilograms. The capital W, total mass of the pontoon with vertical weight, which is 1.16567 kilograms. The x is as stated on the table in the metric of millimeter, and the GM is stated in the table with the metric of also millimeter, with the theta being in degree. This is a table for test 1 with a center of gravity of 132 millimeter and a D of 25 millimeter. This is for the second test with a center of gravity of 104 millimeter and a D of 36 millimeter. And last but not least, the third test with a center of gravity of 80 millimeter and the D of 27 millimeter. Now, we move on for the results and discussion.
Okay, so for result in discussion, we need to plot the graph of GM versus theta. So this is the graph for test 1. So the value of GM that obtained by using the graph for this test 1 is equals to 37.65 millimeter, while for GM obtained by using the area of second moment is equals to 80.67 millimeter. Next. And then we have for test 2. So this is the graph for test 2. And the value of GM obtained by using the graph is 64.23 millimeter, while the GM obtained by using the area of second moment millimeter. And last one, we have test 3. So this is the graph for test 3. So for GM value obtained by using the graph is 81.74 millimeter, while the GM obtained by using the area of second moment is 133.67 millimeter. Next. So, based on GM obtained when theta is 0 by using the graph and GM obtained by using the area of second moment, we can see that the GM obtained by using area of second moment is way larger than the value of GM obtained in the graph for each test. So after that, we compare CG and GM when theta is equals to 0 for test 1, test 2, and test 3 respectively. And by using the comparison above, it shows that the higher the CG, the lower the GM value when theta is equals to 0. Next. Next, we discuss about the reliance of the metacenter on the position of the center of gravity in terms of stability of floating body. So regardless of how a moving body such as submarine is tilted, the metacenter sits slightly above the center of buoyancy. The vessel's center of buoyancy is directly behind the center of gravity, just behind the metacenter while it is at rest on an even keel. The center of gravity is the position in a body where all of the body's parts are balanced. As a vessel tilts, one side of the vessel displays more water than the other, and the center of buoyancy pushes away from the center of gravity and no longer lies immediately underneath it. However, regardless of the volume of tilt, the center of buoyancy resides directly underneath the metacenter. When the ship tilts, the buoyancy restores equilibrium if the metacenter is above the center of gravity. The metacentric height, or the distance between the metacenter and the center of gravity, increases the stability.
The boat is unstable if the metacenter is below the center of gravity, and a tilt results in capsizing. And the last one, we discuss about the effects of variation in angles of tilt on the position of the metacenter. So according to the equation we used before, GM is equals to Wx over W tan theta. The position of the metacenter is inversely proportional to the angle. So as the theta increase, the GM will increase as well. Next, we will move on to the conclusion.
I will continue to present about the conclusion. In conclusion, the height of metacenter is determined using the tilting method. Our data shows that when the center of gravity decreases, the height of metacenter increases. However, the theta obtained is slightly different with the theoretical value due to some errors that we need to overcome. First, we should repeat the measurement and take the average to avoid random error. Next, we should avoid Parras error when taking a point of reading. Lastly, we need to make sure that the primary will stop before taking the point of reading. That's all for our group. Thank you.